Every single color you have ever seen in a gemstone is a lie told by a single atom. And the atom has been telling that lie for 2 billion years without anyone catching it. Let me explain what I mean by that, because this is not a metaphor. This is literally what happened. One element, one type of atom, has been sitting inside crystals, inside pigments, inside your blood, inside the oldest rocks on this planet, quietly doing something that should be impossible. It produces red, then green, then orange, then purple. Not different versions of the element, not different compounds with different metals. The same ion, the same charge, the same electron count. Different color, every single time. I want you to picture a lecture hall, not a big one, a small, slightly overheated room in a university somewhere in Central Europe. Rows of students with notebooks open, pens in hand, waiting for something boring to happen. A woman walks in carrying nothing but a glass flask filled with deep cobalt blue liquid. She sets it on the front desk, says nothing, and picks up a dropper. One drop into the flask. The liquid turns the color of fresh blood. Students look up from their notebooks. Another drop, pale lemon yellow. Someone in the back row laughs nervously because it looks like a stage trick. A third drop. The liquid goes almost black. A deep forest green so dark it looks like something from the bottom of the ocean. Nobody is writing anything anymore. The woman still has not said a single word. She puts the dropper down, looks at the class, and says, "Nothing in that flask changed except the conditions around one type of atom. That atom is element 23 plus 1, 24 protons. That is the entire explanation." The students think she is joking. She is not joking. This is where the real story begins. Because once you understand what that atom is actually doing inside those conditions, once you understand the mechanism, you realize that the same trick it pulls in a laboratory flask is the same trick it has been pulling in rubies, in emeralds, in medieval paints, in the steel of surgical tools, in the groundwater beneath cities, and in rock formations older than any complex life on this planet. The atom does not change. The world around it changes. And that changes everything. Here is what makes this so strange. Most elements behave predictably. You know what you are getting. Iron is magnetic and red when it rusts. Copper turns green when it oxidizes. Silver goes dark. There is a logic to it that feels stable, reliable, almost boring. But this element, number 24 on the periodic table, does something that breaks that intuition completely. It organizes its electrons in a way that almost no other element does. Instead of filling its orbitals in a standard orderly sequence, it rearranges them so that 5 inner orbitals each hold exactly 1 electron. Perfectly symmetrical. Half full. That arrangement is so stable that the element essentially refuses to behave normally from that point forward. And when that ion gets embedded inside a crystal, inside a mineral lattice, inside a paint pigment, the atoms surrounding it create an electric field. That field splits the ion's internal energy levels. The size of that split determines which wavelength of light gets absorbed. And which wavelength gets absorbed determines what color you see. The gap between the ion and its neighbors, a distance smaller than the width of a single atom, decides whether you are looking at red or green. That is the part that should stop you cold. The universe is making color decisions at a scale that no human instrument can directly observe. And this one atom has been exploiting that fact across every context it has ever entered. But here is where it gets darker. Because this same atom that produces beauty in crystals and confusion in laboratory flasks also has a second face. One that is not beautiful at all. One that companies have spent a great deal of money trying to keep quiet. We will get to that, but first we need to go back much further. To a remote mountain range and the piece of rock that traveled across a continent and sat in a cabinet for decades before anyone understood what it actually was. Friends, if you are finding this interesting so far, please subscribe and leave a like. It genuinely helps this channel more than you might think. Now, that orange-red stone. Picture a mining settlement in a cold mountain region, altitude high enough that the air tastes thin, the kind of place where workers spend 10 hours underground and come up blinking at gray sky. One of those workers surfaces one afternoon carrying something that stops him. Not because it is obviously valuable, because it is wrong. The color is wrong. The weight is wrong. The texture when you run a thumb across its face has a density that does not match anything being pulled from these particular rocks. He brings it to the foreman. The foreman sends a sample to a naturalist working in the regional administrative center. The naturalist examines it, describes it carefully, gives it a working name based on its warm, spiced color, publishes a short paper, and then dies unexpectedly before he can investigate further. The circumstances are ambiguous. The mineral, however, survives. Over the following decades, the stone moves. It enters private collections. It sits behind glass in the offices of scientists who find it aesthetically interesting, but chemically confusing. Nobody dissolves it. Nobody heats it. Nobody tries to isolate whatever is making it that color. It is beautiful enough to collect and mysterious enough to ignore. That combination is exactly how important things get delayed. Then, a young chemist in a capital city that is just beginning to recover from a period of intense political chaos gets his hands on a sample. He is not famous yet. He is methodical and precise, and he has been trained to follow a reaction wherever it leads, rather than stop when it confirms his expectations. He dissolves the mineral in acid. He runs a series of careful steps, and at the end of the process, he has something on his bench that does not match any known substance. A gray metal, hard, with a faint bluish shine when the light catches it at the right angle. He runs more reactions. Each one produces a compound of a completely different color. Orange, yellow, deep green, violet. He does not know what he is looking at yet, but he knows he is looking at something that has never been named. He names it after the Greek word for color, because that is the only word that fits. This is not a metal that does one thing. This is a metal that does everything, depending entirely on what you put around it. And that naming decision, made in a small laboratory with rudimentary equipment, turns out to be the most accurate scientific naming in the entire periodic table. Not because the metal is colorful in a decorative sense, but because color is literally a record of how atoms interact with the energy around them. And no atom on the entire table is more sensitive to that interaction than this one. What the chemist stumbled onto was not just a new element. He stumbled onto a new principle. That the same thing in different contexts is not the same thing at all. He did not fully understand that yet. Neither did anyone else. But the stone from the mountain had been trying to tell that story for years, sitting behind glass in cabinets across the continent, waiting for someone patient enough to dissolve it. The chemist who named this element after color had no idea he had just described the most deceptive atom in existence. And the deception goes so deep that it fooled physicists for nearly 2 billion years before anyone figured out what was actually happening. So let me take you back to that small laboratory. The gray metal is sitting on the bench. It has been isolated, weighed, tested. It is real. It is new. And the chemist, whose name was recorded in European scientific journals of that era, but who never became the household name he deserved to be, begins working through its compounds one by one. He is not rushing. He has the kind of patience that only people who genuinely love the process can sustain. He prepares one compound and notes its color, prepares another and notes a completely different color, then another, then another. By the time he finishes his first systematic series of experiments, he has produced more distinct colors from a single element than most chemists see in an entire career working across dozens of elements. He writes in his notes something that translates roughly as, "This substance seems to carry within it the entire spectrum." He means it as a poetic observation. He does not yet know it is a precise physical description. The compounds travel. Other scientists in other cities receive samples. The reaction is consistent. Every single person who works with this metal for the first time has the same experience. Confusion, then fascination, then a kind of unsettled feeling that the rules they thought they understood are slightly more flexible than they appeared. That feeling is correct, but the explanation for why it is correct will not arrive for another century and a half, when physics develops the tools to look inside the atom itself. Here is what those tools eventually revealed, and I want you to stay with me here, because this is the part that changes how you see every colored stone you have ever held in your hand. The atom at the center of this story organizes its electrons in a configuration that prioritizes internal symmetry above the normal rules of orbital filling. 5 inner orbitals, each holding exactly 1 electron, arranged like spokes on a wheel. Perfectly balanced. The kind of arrangement that nature finds so stable it will bend its own standard rules to achieve it. And that symmetry is the source of everything strange that follows. When this ion sits inside a crystal, the atoms around it push on it electrically. That pressure, that surrounding electric field, forces the ion's inner energy levels to split apart. Some levels get pushed higher, some get pushed lower. The gap between those levels corresponds exactly to the energy of a specific color of light. The ion absorbs that color and reflects everything else. What you see is the remainder. The color that the atom did not want. Now here is the part that should genuinely disturb you. 2 of the most famous and valuable gemstones in human history, stones that have been traded, stolen, worn by rulers, and fought over across thousands of years, both get their color from this exact mechanism. Both contain the same ion of the same element in the same chemical state. One produces red, one produces green. They sit at opposite ends of the visible spectrum, separated by more than 150 nanometers of wavelength. And the only reason they look different is a gap between atoms that is smaller than a single nanometer. We are talking about a distance so small that the best microscopes of the 19th century could not have begun to detect it. A distance that makes the difference between the most prized red stone and the most prized green stone on Earth. The universe made that color decision at a scale that was completely invisible to every human being who ever admired either of those stones, right up until the moment modern physics built instruments capable of measuring it. Think about what that means. Every jeweler who ever appraised those stones, every monarch who ever wore them, every poet who ever wrote about their color, all of them were responding to a phenomenon happening at a scale they had no concept of, caused by an atom arranging the light around it in a way nobody understood yet. The beauty was real. The response was real. But the explanation was hidden inside a layer of reality that human perception simply cannot reach. And here is what makes this even stranger. The element does not care which crystal it is sitting in. It is not trying to produce red or green. It is just responding to its environment with perfect mechanical honesty. The color is a side effect of physics, not an intention. Which means every ruby that has ever existed, every emerald, every piece of jewelry built around these stones, is essentially a visible record of an invisible distance. A color that is really just a measurement, expressed in light. The chemist with his bench full of colored compounds did not know any of this. He just knew that the metal behaved unlike anything he had encountered. He named it and moved on. But the question he inadvertently raised, why does the same atom look different in different places, turned out to be one of the most productive questions in the history of chemistry. It pushed scientists toward quantum mechanics. It forced a rethinking of what color actually is. And it eventually revealed something that nobody expected at all. That this same atom, this compulsive color changer, had been quietly recording the history of the entire planet inside ancient rocks for billions of years. But before we get there, we need to talk about a painter who trusted this element with his most important work and paid a price he never lived to see. The painter was not a minor figure. He was someone whose use of color was considered almost aggressive in its intensity, someone who chose pigments the way other people choose weapons. He wanted his yellows to hit the viewer like a physical force. And when a new synthetic pigment became available that offered exactly the shade he was after, a yellow so saturated it almost vibrated off the surface, he used it without hesitation. He used it everywhere. On canvases that would eventually hang in some of the most visited museums on Earth. He layered it, mixed it, built entire compositions around its particular frequency of light. He had no way of knowing that the element responsible for that yellow existed in a chemically unstable state inside the pigment. No way of knowing that exposure to light, ordinary daylight falling on a painted canvas over decades, would slowly trigger a transformation in the atom's internal configuration. The same mechanism we just described, that split between energy levels, that sensitivity to surrounding conditions, was working against the painting from the moment it dried. The yellow began to change. Not suddenly, not dramatically, slowly, the way a season changes, so gradually that no single day looks different from the last. The bright, saturated yellow started deepening, then darkening, then shifting towards something brownish, muted, like a color that has been left out too long and lost its conviction. By the time researchers began systematically studying the pigment chemistry of these paintings, more than a century after the painter's death, the damage was already extensive and completely irreversible. A team working with instruments that could analyze the chemical state of pigment without touching the canvas surface confirmed what the colors already suggested. The element inside the yellow had converted. Its energy configuration had shifted. The light it absorbed had changed. And therefore, the light it reflected had changed. The paintings that hang in museums today, the ones that millions of people travel specifically to see, are not the paintings the artist made. They are a later version. A version rewritten by an atom responding to its environment over 130 years of exposure. The artist spent his life trying to capture light. The element he chose to do it with spent the century after his death quietly rearranging that light into something he never intended and would never have recognized. That is not carelessness. That is not negligence. That is the atom doing exactly what this atom always does. Responding to conditions. Changing its behavior. Producing a different output in a different environment. The same principle that makes a crystal red instead of green, applied to a canvas. Applied to an artist's legacy. Applied without permission and without warning. And if you think that is the most damaging thing this element has ever done without anyone noticing, you are not even close to the worst part of this story yet. The entire foundation of modern surgery was discovered because a man forgot about a pile of metal scraps in the corner of his workshop. And if he had been slightly more organized, none of it would have happened. I want you to sit with that for a second. Every sterile surgical instrument that has ever entered a human body, every food pipeline that has ever carried something you ate, every implant-grade component that has ever been fitted into a joint or an artery, all of it traces back to a moment of pure accidental neglect in a metallurgy workshop in the industrial north of England in the early 20th century. The man working in that shop was not a visionary. He was a practical engineer with a specific brief. His employer needed a better-performing alloy for a mechanical component that was degrading too fast under repeated stress. The engineer spent months casting test samples, measuring their performance, rejecting the ones that did not meet the required specifications, and stacking them in a corner of the workshop to be dealt with later. He was methodical. He kept records. He had no interest in accidental discoveries, because accidental discoveries were not part of his assignment. Then one afternoon, he walked past that corner pile and stopped. Most of the samples had developed the reddish-brown surface texture that metal gets when it has been sitting in humid air too long. Rust. Normal, expected, unremarkable. But a small cluster of samples near the back of the pile looked completely untouched. No discoloration. No surface change at all. They looked like they had been cast that morning. He picked one up and turned it over in his hands. The surface had a faint, cool sheen, almost like the metal was still slightly wet, though it was completely dry. He checked his records. Those particular samples all had one thing in common. Their chromium content was above a specific threshold. He ran the experiment properly. He cast new samples at varying chromium concentrations, exposed them to the same conditions, and waited. The results were completely consistent. Below a certain chromium level, the metal rusted. Above it, nothing happened. The surface stayed clean, smooth, unmarked. He did not immediately understand why. The explanation came later, from chemists rather than engineers. What happens at that chromium threshold is that the element spontaneously builds a protective layer on the metal surface. Not a coating you apply, not a treatment you perform. A layer that forms itself automatically from the chromium atoms already present in the alloy, the moment they contact oxygen in the air. The layer is transparent, which is why the metal still looks like metal. And it is self-repairing. Scratch through it, and within seconds, it rebuilds. The chromium in the alloy migrates to the damaged area and closes the gap. That invisible self-healing film, thinner than any instrument of that era could measure, is what changed everything. Before this discovery, the tools used in medical procedures were cleaned and prepared as carefully as possible. But the metal itself was always fighting a losing battle against moisture and oxidation. After this discovery, a new class of alloys became possible where the surface chemistry worked in favor of cleanliness rather than against it. The implications spread outward into every industry that needed durable, contamination-resistant metal surfaces. Chemical processing, food production, marine engineering, aviation. The entire modern built environment carries this accident inside it. And here is what strikes me every time I think about this. The engineer was not looking for this. He was not even curious about it until he happened to walk past a pile of forgotten metal on a day when the lighting in the workshop was right to show the contrast between the rusted samples and the clean ones. Change the lighting, change the time of day, change the direction he walked into the workshop. The discovery does not happen, or it happens 20 years later, somewhere else, by someone else. The history of materials science has a corner pile of forgotten samples at its foundation, and that pile exists only because one engineer was slightly behind on his cleanup. But accidental or not, the discovery was real, and its consequences were immediate and enormous. Which brings me to something that almost nobody mentions when they talk about this element. Because around the same time that corrosion-resistant alloys were beginning to transform industrial manufacturing, governments and military planners were quietly waking up to a different dimension of this element entirely. Not its chemistry, its geography. Where it existed in the ground, in what quantities, and who controlled access to it. The painter whose yellows were slowly darkening on museum walls never knew that the same element in his pigment was simultaneously becoming one of the most strategically important materials on Earth. That a metal whose behavior changes entirely based on its surrounding conditions was about to demonstrate that principle not just in a crystal or on a canvas, but on a map. And the story of what happened when armies and governments started competing for control of this element is considerably darker than anything we have covered so far. The word that strategists used, quietly, in planning documents that were not made public for decades, was dependency. who was dependent on whom, and what happened when that dependency was weaponized. Here is how it worked. High-performance armor requires a specific set of properties that standard steel cannot deliver. It needs to absorb impact without shattering, hold its structural integrity under repeated stress, and resist the kind of surface damage that degrades performance over time. Chromium in the alloy is what delivers those properties. Without it, the metal is harder in some ways, but more brittle. It fails differently. It fails worse. And in a conflict where the quality of armored vehicles determines how far an advance can push before it stalls. The difference between high chromium armor and low chromium armor is not a technical footnote. It is an operational reality measured in territory and casualties. The problem for one of the major industrial powers of the mid-20th century was simple and serious. There was no significant domestic source of chromite ore within its borders. The entire supply had to come from outside, and the suppliers were not neutral parties with no interest in the conflict. They were countries with their own calculations, their own pressures, their own interests in keeping multiple sides of the conflict dependent on their cooperation. One supplier in particular became the focus of years of intense diplomatic effort by both sides. This country sold ore to one side while receiving pressure from the other to stop. It played both angles with considerable skill for an extended period. Extracting economic and political concessions from each direction. Intelligence services from multiple nations were actively working to influence its decisions. Economic analysts were calculating exactly how many months of production the dependent power could sustain if the supply was interrupted. Military planners were modeling what the quality degradation in armored vehicle production would look like 6 months after supply stopped, 12 months after, 18 months. The numbers were not encouraging for the side without domestic ore. When the supply was eventually reduced, the war had already shifted in ways that made the metallurgical constraint one factor among many. But the fact that senior planners on both sides treated chromite access as a first-tier strategic problem, the same category as fuel and food and communication lines, tells you everything about how seriously this element was taken behind closed doors. And then the war ended. And the strategic calculus did not disappear. It just changed shape. Because the largest known deposits of chromite on Earth were concentrated in a region of southern Africa that was about to become the center of a very complicated geopolitical argument. And the element that had quietly shaped the industrial capacity of warring nations was about to become a different kind of weapon entirely. One that did not require armor or alloys or engineering at all. More than 70% of the world's chromite reserves sit inside a single geological formation in southern Africa. And during the Cold War, Western military planners had a classified scenario document dedicated entirely to what would happen if that formation fell under hostile control. They called it the dependency problem. The answer they kept arriving at was not reassuring. Let me put that in concrete terms. The industrial capacity to produce high-performance alloys, the kind used in aircraft engines, in naval vessels, in the cutting tools that manufacture every precision component in a modern economy, all of it runs through chromite. And more than 2/3 of the known supply of that ore was sitting in one place. A place that was, at that particular moment in history, politically unstable, internationally contested, and actively being courted by opposing sides of the most consequential ideological standoff the modern world had seen. The geological formation itself is ancient. It formed when an enormous volume of magma intruded into the existing rock structure and cooled in distinct horizontal layers over millions of years. Those layers settled into bands, each one chemically distinct, some carrying platinum, some vanadium, some chromite in concentrations that made every mining engineer who ever surveyed the region go quiet for a moment before saying anything. The ore body is not just large, It is dense, accessible, and consistent in a way that made it irreplaceable at a time when no viable alternative source had been identified at comparable scale. Western governments were in a position they had created for themselves over decades. They publicly criticized the political regime controlling this region. They passed statements, applied selective pressure, made speeches about values and international standards. And simultaneously, their industries continued purchasing ore from the same region, because the alternative was accepting a strategic materials gap that their defense and aerospace sectors could not absorb. The hypocrisy was not accidental. It was calculated. Someone in every relevant government had run the numbers and decided that the ideological cost of continued purchasing was manageable in a way that a chromite shortage was not. Meanwhile, on the other side of the Cold War divide, a different power was watching this situation with considerable interest. This power had spent years building relationships across the African continent, supporting independence movements, providing technical assistance, establishing economic partnerships with newly formed governments. The diplomatic and intelligence effort was substantial, and chromite access was not incidental to that effort. It was one of the primary objectives beneath the surface of the public narrative. Strategic planning documents from this period, some of which have since been declassified and studied by historians, show analysts working through scenarios with names that read like thriller chapter titles. What happens to Western aircraft production if Southern African chromite exports are redirected? How many months before manufacturing bottlenecks appear? Which components fail first? The calculations were precise, the conclusions were stark, and the element at the center of all of it was the same one that a forgotten chemist had named after color because he could not stop it from producing a different shade every time he touched it. That is the part I keep coming back to. The same instability that makes this atom beautiful in a crystal, the same context sensitivity that destroyed a painter's yellows over a century of light exposure, is the same property that made it irreplaceable in industrial alloys. You cannot substitute it, because nothing else does exactly what it does under those exact conditions. And that irreplaceability is what turned it from a chemical curiosity into a geopolitical instrument. The atom was not designed for any of this. It just responded to its environment. Humans built entire systems of power around that response. The Cold War eventually ended. The political situation in the ore regions evolved. The dependency calculations were revised, new sources were developed, and the scenario documents quietly moved from active planning files to historical archives. But the underlying reality did not change. The ore is still concentrated where it always was. The industrial need is still real. And the question of who controls access to critical materials in the ground has not become less relevant. It has become more relevant. Different materials, different regions, same structure. The atom changed its context again. The lesson did not change at all. And now I need to tell you about what happens when this element stops being useful and starts being actively harmful. Because we have spent a lot of time on the constructive side of its chemistry. The corrosion resistance, the color in gemstones, the strategic value of its ore. But this element has another face, and it is considerably harder to look at. The toxic form of this element, the form it takes in certain industrial processes, was being used in manufacturing operations across multiple countries for decades before the health consequences became impossible to ignore. And the story of how those consequences were documented, contested, and eventually forced into public view is one of the most important examples in modern history of what happens when the chemistry of an industrial process meets the biology of the people living near it. It starts with a property we already understand. The self-healing protective film that makes chromium alloys corrosion-resistant also works in cooling systems, in industrial water circuits, in any closed loop where metal components need to be protected from oxidation. The compound used for this purpose contains the element in its toxic form. It is effective, it is relatively cheap, and for a long time it was considered a manageable risk because the assumption was that the water containing it would stay where it was put. That assumption was wrong, and the people who paid the price for that error were not the engineers who designed the systems or the executives who approved them. They were the families living in the houses above the groundwater. Picture a small town in a dry inland region, not a place that appears on lists of anywhere important. Dusty roads that turn pale gray in summer heat. Gardens that need constant watering because the climate does not cooperate. Children who grow up drinking water from wells that have been in their families for generations. The town has a large industrial facility on its outskirts that has operated quietly for years, employing local workers, paying local taxes, existing as the kind of permanent background presence that towns built around single employers tend to normalize completely. The facility uses chromium compounds in its cooling water. The water is discharged into containment areas. The assumption, built into the original engineering design, is that the containment will hold and the compound will not migrate. What actually happens is that the compound filters slowly through the soil over years, following the path of least resistance downward into the aquifer that feeds every well in the surrounding area. The process is invisible. There is no color change in the water, no smell, no immediate physical effect that would alert anyone that something has changed in what they are drinking. The residents drink this water for years, some for more than a decade, and during that time, the element moving through their bodies is doing something at the cellular level that we now understand in considerable detail. The toxic form of this element is shaped in a way that biological transport systems cannot distinguish from a common and harmless ion that cells move routinely. The cell membrane waves it through. Once inside, the element begins converting to its less toxic form, and during that conversion, it releases reactive particles that interact with DNA in ways that cause damage. Strand breaks, structural alterations, the kind of changes that, accumulated over sufficient time and exposure, shift the probability of certain serious illnesses in a direction nobody chooses. The elevated rates of illness in communities near these contaminated sites were not immediately connected to the water. They appeared gradually, statistically, as patterns in medical records that only became visible when someone started comparing numbers across the whole community, rather than treating each case as isolated. The connection required someone willing to ask an uncomfortable question about what all these cases had in common. And asking that question required someone with no particular institutional interest in not finding the answer. In the town I am describing, that person was not a scientist or a regulator. It was an ordinary person who worked in a legal office, noticed an anomaly in some documents, and decided to pull the thread. What unraveled when that thread was pulled was not just a local contamination story. It was a demonstration of how thoroughly the industrial use of this element had been managed in ways that prioritized operational convenience over the health of the surrounding population, in multiple locations, across multiple decades. The legal process that followed established new records for environmental settlement amounts at the time. The company involved reached agreements with hundreds of affected residents without formally admitting the causal connection that the science had already documented. And the groundwater beneath that town continued to carry elevated concentrations of the toxic form of this element for years after the legal resolution. Because the chemistry of contamination does not resolve on the same timeline as a legal settlement. The atom, again, was just responding to its environment. Moving through soil the way water moves through soil. Crossing cell membranes the way the right-shaped ion crosses cell membranes. Doing exactly what its chemistry dictates, without malice, without intention, without any awareness of the consequences. The decisions that put it in the groundwater were human decisions. The chemistry was just chemistry, but the outcome was human. In the most irreversible way. And somehow, after everything we have just covered, this same element still has at least two more completely unexpected stories to tell. The first beam of coherent light in human history was produced by an atom that everyone in the scientific establishment had already written off as useless for exactly that purpose. And the man who proved them wrong never received the award that everyone agrees he deserved. Let me set the scene properly. We have just spent time with chromium as a geopolitical instrument, as an industrial material, as a slow-moving threat in groundwater. Now I want to take you somewhere completely different. A private research laboratory on the California coast, late afternoon. The kind of light that comes through west-facing windows and sits low and golden on every surface. A young physicist in his early 30s is working alone on a setup that his colleagues have collectively and repeatedly told him is a dead end. His name is not important for our purposes. What is important is that he has a doctorate from one of the most respected technical universities in the country. He has applied for research funding and been turned down because the review committee considered his chosen approach fundamentally flawed, and he has decided to continue anyway, using whatever resources his employer will allow him access to on his own time. That combination of credentials, rejection, and stubborn continuation is the exact profile that appears over and over again in the history of genuine scientific breakthroughs. Institutions are very good at identifying what the current consensus considers promising. They are much less good at identifying what the current consensus has gotten wrong. The device he is working on sits on a bench about the length of a kitchen table. At its center is a synthetic crystal, cylindrical, roughly the length of 2 fingers placed end to end. The crystal is pale pink, almost colorless in ordinary light, but when you hold it at a certain angle, it catches the wavelength coming through the window and throws back a faint red warmth. That color is chromium. Specifically, it is chromium ions embedded inside the crystal lattice of synthetic ruby, producing exactly the phenomenon we described earlier, absorbing green light, reflecting red. Around this crystal, the physicist has wound a spiral flash lamp, the same component used in commercial photography equipment. Simple, available, cheap. The rest of the setup is mirrors, electronics, and careful geometry. One mirror at each end of the crystal, one fully reflective, one allowing a small percentage of light to pass through. The whole apparatus looks, frankly, like something a determined amateur built in a garage, which is essentially what it was. He runs the power up. The flash lamp fires. White light floods the crystal from all sides simultaneously. The chromium ions inside absorb the green component of that light, and their electrons jump to a higher energy state. Then, through an intermediate level, where they pause for a brief but measurable interval, they begin releasing that energy as red light. Photons of red light bounce between the 2 mirrors, passing through the crystal again and again. Each pass stimulates more ions to release their photons at the same moment, in the same direction, at the same wavelength. The signal builds. The avalanche reaches a threshold, and through the partially transparent mirror at one end, a pulse of red light exits the crystal in a single coherent beam. The physicist measures it, checks his instruments, runs it again. The result is identical. He sits with that for a moment in the low afternoon light, in a quiet laboratory that smells faintly of electronics and warm metal, and understands that he has just done something that has never been done before in the history of physics. He has produced a beam of light in which every photon moves together, same direction, same wavelength, same phase. Light that does not spread or scatter. Light that carries energy with the precision that nothing in nature produces on its own. He writes up the results and submits them to one of the most prestigious physics journals in the world. The editors decline to publish. Their reasoning is that the field of light amplification has attracted too many speculative submissions, and they are not convinced this one is sufficiently differentiated. The paper that describes the first laser ever built is rejected by the journal that should have published it. It eventually appears in a British publication, and within months, the scientific community understands what has happened. Within years, the applications begin multiplying in directions nobody had fully anticipated. Precision manufacturing, surgical procedures, communications infrastructure, measurement at scales previously impossible. Every one of those applications traces back to a crystal the size of 2 fingers wound in a flash lamp, built by a man who had been told he was wasting his time. The Nobel Prize for the theoretical foundation of laser technology was awarded a few years later. The physicist who built the first working device was not included. The committee gave the prize to the theorists. The decision generated controversy that has not fully dissipated in the decades since. The man who actually made the light did not get the recognition. The chromium ions in his crystal did not care either way. They just did what they always do, responded to the energy around them and produced something nobody expected. And now I want to take you somewhere even further back. Not decades, not centuries. Billions of years. There are rocks on this planet that are older than any complex life that has ever existed. They sit in outcrops in southern Africa, in the Canadian Shield, in the ancient cores of the Australian continent, and they have been accumulating in layers since before the first animal drew breath. Before the first plant converted light to energy, before the ocean chemistry that supports all complex biology existed in anything like its current form. These rocks are an archive. Every layer is a record of conditions that existed when it was deposited. Temperature, chemistry, atmospheric composition. Read carefully enough, they tell a continuous story of how this planet transformed itself over time. Chromium is one of the most precise readers of a specific chapter in that story. Here is why. This element behaves completely differently depending on whether free oxygen is present in the surrounding environment. In the absence of oxygen, it stays locked in its insoluble form, sitting in minerals, going nowhere, leaving no trace in the water or the sediments forming nearby. When oxygen is present, it converts to its soluble form, moves with water, reaches the ocean, and deposits into the sediment layers forming on the seafloor. That transition leaves a measurable chemical signature in the rock, not a visual one, not something you can see by looking at the stone. A signature in the ratio between different versions of the same atom, different weights of the same element, that can only be read with instruments that did not exist until recently. Geochemists working across multiple continents began comparing that signature in rock samples of different ages. The pattern they found was consistent everywhere they looked. Below a certain age threshold, the signature is absent. The element left no soluble trace in the ancient seafloor sediments. Above that threshold, the signature appears, sharp, clear, reproducible across samples separated by thousands of kilometers. And the age at which that transition occurs, the moment when this element first began moving through the ancient ocean in detectable quantities, corresponds precisely to the moment when other independent lines of evidence say that free oxygen first accumulated in the atmosphere at meaningful concentrations. That moment is called the Great Oxidation Event. It happened approximately 2.5 billion years ago. Photosynthetic microorganisms had been producing oxygen as a metabolic byproduct for an extended period before that. But for a long time, other chemical reactions in the environment consumed the oxygen as fast as it was produced. Then, the balance shifted. The oxygen began to accumulate. The atmosphere changed. And for the majority of the life forms that existed at that point, life that had evolved in an oxygen-free world and had no defenses against it. This was catastrophic. Oxygen is chemically aggressive. It damages biological molecules that are not built to handle it. Most of the anaerobic organisms that had populated every corner of the planet simply could not survive the transition. What came after is everything. Every aerobic organism, every complex cell, every animal, plant, fungus, and visible living thing in the history of this planet. All of it is downstream of that atmospheric shift. And chromium, sitting in ancient sediments on 3 continents, recorded the exact moment it happened. The same atom that colors gemstones and destroys paintings and protects surgical steel and poisoned groundwater in a quiet desert town also contains, locked in its isotope ratios, the timestamp of when life as we know it became chemically possible. Think about the full arc of what we have covered. A strange orange mineral pulled from a mountain nobody had heard of. A gray metal named after color because it refused to stay the same. A painter's yellows darkening across a century without anyone's permission. Forgotten metal scraps in a workshop corner that changed the history of medicine. Classified documents about ore deposits and military dependency. Communities drinking water that carried invisible damage. A physicist alone in a coastal laboratory producing a beam of light that nobody believed was possible. And ancient rock layers holding a chemical memory of the moment this planet first learned to breathe. Every one of those stories is the same story, an atom responding to its environment with absolute consistency, producing different outcomes not because it changed, but because everything around it changed. Context is not a footnote to the story of this element. Context is the entire mechanism. What chromium does depends entirely on where it is, what surrounds it, what conditions it finds itself in, and the outcomes range from the most beautiful things human beings have ever created to some of the most serious harm we have caused without intending to. Here is the question I want to leave you with, and I want you to think about this genuinely before you answer. If the same atom, under different conditions, can be the color inside a ruby and the contamination in a child's drinking water, then what does that tell us about how we decide which uses of a material are acceptable and which are not? Is that a chemistry question? Is it an ethics question? Is it a question about who has the power to decide what conditions other people live under? Write what you actually think in the comments. Because this question does not have a clean answer, and I am genuinely curious whether you think it ever could. If this story made you see something differently, please leave a like and subscribe to the channel. There are more stories like this one, and every single one of them starts with a question that looked simple until someone looked closely enough.